Okay, good morning, everyone. Continuing with our discussion on chapter 3, capacitors and inductors. We'll look at the voltage and current equations for an inductor today, and we'll also introduce the topic of capacitors. So, first up is the physical construction of an inductor. Any piece of current carrying conductor wound in a spiral coil is an inductor, right? It has a established magnetic field. If current passes through it and you have several loops or several turns, the magnetic field strength increases. So the physical construction of an inductor is simply a coil of current carrying conductor. Okay, it's simply a coil. The equation is given by L equals mu n square A over L. The uppercase L stands for the inductor value. Lowercase l is the length of the inductor measured from end to end of the spiral coil. Okay, measured from end to end of the spiral coil. So this is the lowercase l. It looks like a 1, but it's an L. Okay, so lowercase l. And notes the length in meters. A is the cross-sectional area of the coil, which is from here to here. And of course, you can take the radius of that loop and calculate the area. N is the number of turns, basically the number of loops that you have in the inductor. Okay, the higher the number of loops, the higher your inductance. Basically, inductor value and capacitor value, again, has to do with the capacity to store the energy, right? So the more number of loops you have, the higher the inductance. And then, of course, the core of the inductor, meaning the center of the loop, center of the spiral coil, is known as the core of that inductor. There can be air core inductors or could be ferromagnetic materials. You could insert iron, nickel, cobalt, any kind of magnetic material which has high permeability. Permeability is the ease with which magnetic flux lines can be established through that core or through that material. So as we saw in the previous slide, not in this one, 2 slides ago, if you only have air through the spiral coil, the magnetic field strength is weak. But if you insert a material in there which has high permeability, the magnetic flux lines can be established much stronger with ease, and the magnetic field strength increases. So the inductance value also increases. And that is noted by the term mu, the Greek letter mu, lowercase mu. It's defined as the permeability, and mu in turn is a product of mu 0 and mu r. Mu 0 is the permeability of free space. Mu r is the relative permeability of that specific material relative to free space, or relative to the permeability of free space. So again, this is the permeability of free space, and this is relative permeability of the material with respect to mu 0. It's a material property, so it changes depending on the type of material we use. Iron, steel, cobalt, nickel, they all have permeability that are hundreds or even thousands of times that of free space. And because it is a comparison with relative to mu 0, mu r actually is dimensionless. It does not have any units. Now, again, equations you can have on your equation sheet. Be familiar with those equations. You should only know how to actually use those equations. So if a question comes in a quiz or in an exam, trying to figure out the inductance of a given specific construction, you should be able to know, extract information, and then apply the equation and calculate the final values. Okay, yes. Area is the cross-sectional area of this loop. Depending on how big or small the area is. So the only thing that decreases the inductance is the length. Okay, the longer the loop, the lower the inductance. Everything else increases the inductance. So the inductance value is directly proportional to the number of turns, is directly proportional to the permeability of the core, and is also directly proportional to the cross-sectional area. In real life inductors, the value of inductances that we use in electric and electronic circuits is very small. It's millihenries, sometimes even microhenries. On a side note, capacitors are even smaller than that. Okay. So real life inductors, if you want big ones, we have big coils. The reason is, of course, to have a usable value of inductance, the size, the cross-sectional area of the loop has to be larger. Make sense? Right? Okay, so that's enough about the equation. Just a few examples of what a real life inductor looks like. If you've ever seen resistors in real life, tiny resistors, these are about the size of tiny resistors. These are pretty big, as you can see. Look closely at the values of these inductances. Okay, you see the number of turns in here is much less. In the first one, sorry, this one right here. Number of turns is much less. So the value of the inductance is also less, 10 microhenry. However, notice the thickness of that wire. Notice the thickness of this coil compared to the one in the middle. Okay, that thickness has high capability, has capability to carry high current. So the current carrying capability of this is 10 amps. 10 amps is a huge amount of current. Typical electronic circuits, the current is in the order of like milliamps. Okay, milliamps. So 10 amps is a huge amount of current. So depending on the construction, this is a thinner wire, so lower current carrying capacity, but the number of turns is much more compared to that first one. And so the inductance level is about 100 times that of the first one, 1 millihenry versus 10 microhenry. Okay, and then we increase the construction and size, and then you have 1 millihenry plus a higher current carrying capacity. Okay, so just a few examples of real life inductors where you can change the physical dimensions of your components, and you can change the current carrying capacity as well as the inductance level of that inductor. All right, yes. There is no current in there. So the current has to do with the cross-sectional area of the actual material. So if this is the material, of that coil, it has to do with the resistance of the coil and the material that is used to actually make the coil. So the current does not affect the value of the inductance. It's a separate spec, right? It's a separate specification. 10 amps and 10 microhenry. All right, now we come to the main stuff, the VI equation, the voltage and current equation. For an inductor, we always talk in terms of the input current, okay? And remember I mentioned in last class, if the current input through a inductor is constant, right? Then the voltage across the inductor would be 0. So it's always measured in terms of the change in current. When current changes, it is receiving energy or it's either discharging energy. And so the equation for voltage and current for an inductor is V equals L di over dt. The voltage is directly proportional to the rate of change of current that is flowing through it. Okay, rate of change of current, di over dt, change of current with respect to time. And again, we now journey into the time domain. So the equations that we deal with are a function of time. So again, voltage is directly proportional to the rate of change of current. So di over dt, and the constant is the inductance value. Okay. So V is directly proportional to di over dt. Multiplied by the constant, which is the inductor value. So V equals L di over dt. Again, on a side note, when we get to the capacitor, that equation also has a similar setup to the same VI equation. Okay, voltage for an inductor is L di over dt. So the flip side of that is if you're given the voltage and you wish to find the current, you simply integrate both sides. L is a constant, comes outside, you integrate the current, you take everything else on the other side, and you get V, integral of t, integral of V with respect to t. And because you're integrating, basically you're summing up everything, right? You're summing up each individual slice. So when you're summing it up, you sum up from the beginning to the end t. So in this case, t0 does not mean the beginning of time. It simply means the time when you begin or you began analysis. Okay. You could have a system and you could be analyzing from, let's say, 0 seconds to 10 seconds. But if you wanted to look at a small piece of that time interval, let's say from 5 to 7, so t is equal to 5 seconds, and then you wish to find the voltage from 5 to 7, that t equals to 5 seconds would be your initial time, the time at which you began your analysis. Does that make sense? So even though it says t0, t0 could have any value. Okay, within a time interval or a time frame, that t0 is the point in time where you begin your analysis. And then this t is the variable. Typically, when you wish to end your analysis. So as I said, as an example, if you were analyzing a system between the time periods from 0 to like 10 seconds, and you wish to look or calculate voltage or current for particular time, for example, between 5 and 7, t0 would be 5, your endpoint would be 7. All right, any questions? Yes. Where? Here? Oh, this one, yes. This is 1 over L. So this is when we integrate L di over dt. L comes outside, take it on the other side, becomes 1 over L integral of V. So I of t, the current as a function of time, is given by 1 over L, reciprocal of L, because we on the other side, an integral of the voltage of that inductor from time t0 to t. I will talk about this a little bit just after. Okay, it's simply the flip side of the VI equation. Voltage is di over dt, so current is integral of V. That's all it is at its basic. Does that make sense to everyone? Everyone remember this from what? Calculus 3, Calculus 4? Where do you learn this? 2? Okay, integrals 2. All right. But this is as far as we go. We don't go too much in depth. Okay. What do you think I of t0 means? Remember, we are talking about voltage and current as a function of time, right? V of t, I of t. It's the initial current that is actually present in the inductor, right? And this is a very important concept because we say, not because capacitors and inductors are energy storage devices. When you're performing circuit analysis, there could be a time, there's always a time where the inductor or capacitor already had some stored energy. Okay, so if you are accounting for the total current for that inductor from a certain point in time, then you also have to account for the energy that was previously stored in that inductor. Remember, I just used the example of a system that is going from 0 to 10 seconds, right? And we wish to look at a small slice of that from, let's say, 5 to 7 seconds. So if we wish to find the current at 5 seconds from 5 to 7, right, we integrate between 5 and 7, but we have to account for the current that might be present at time t equal to 5 seconds. So I of t0 in that case, my 5 would be t0. And so I of t0 would be the initial stored energy in the inductor. Initial stored energy in the inductor. And that is what that I of t0 is. And it would pretty much be a constant. A value would be given, well, given in the sense, the value would be there in the problem statement. It would be up to you to actually recognize it and extract that information. But there would not be any calculation that you would need to do. Yes. No, it's I is the value of I at time t equals 0. But time t equals 0 again is not, it's not this. It is simply the time where you're beginning your analysis. So again, you could divide a big time frame into small pieces, and every piece would have a beginning. And so t0 for every piece would be different. All right, let's take a 10-second pause. Think over that. Let me know if you have any questions. Again, we won't go, remember, this is a non-EE major class, so we just do snorkeling. We are not going scuba diving. Right? So we're going to skim the surface. We look at these equations, understand the equation, and know how to apply it. And that's all I would ask of you. All right, any questions? Okay. All right, then let's move on. Power and energy. Oh, actually, no, before we get to power and energy. Important point here. Remember, I said if you apply a constant voltage or a constant current to an inductor, the voltage is 0. Quantitatively, we know V equals L di over dt. If I doesn't change, if I is a constant, V is 0, right? Rate of change of current. If the current is not changing, voltage is equal to 0. Mathematically, it works out or it checks out. So if you have a DC source, a battery, for instance, right? Any kind of DC source, DC is constant. Value does not change with respect to time. And this is time on the x-axis, and this is voltage on the y-axis, or current, voltage or current. If you have a value, whatever that value is, remains the same. If you take a 1.5 volt battery, that 1.5 volt battery is going to stay the same, well, depending on the electrochemical reactions. But when you connect it to a circuit, it's going to supply 1.5 volts. So constant with respect to time. Constant or fixed value. It doesn't change. Now, remember what I said at the introduction of this chapter. Energy cannot be transferred instantaneously, right? So if you apply a current of, let's say, 1 amp, right? Inductor has 0 energy stored. It cannot go instantly from 0 to 1. It'll take some time for it to charge. And that charge or that curve is exponential in nature. And we will look at those equations in chapter 4. Okay. So if the inductor was being applied this current right here, it would, let's use, what do I want to use? Let's use red. The inductor would follow a pathway something like this. Okay, it cannot go instantaneously from 0 to 1. So this will be the inductor receiving the energy or charging. Once it reaches the max value, that max value is known as steady state. Because the value for the voltage is at a steady level. Okay, steady level. So anytime we apply a DC voltage or current to a capacitor or an inductor, we say that it will reach steady state. And the steady state behavior is that the voltage for an inductor would be 0. For a capacitor, conversely, at steady state, current I would be equal to 0. And we'll look at that in just a few slides. For an inductor, when you apply an input current, a DC current, after the initial transient portion, once it reaches full charge, meaning the inductor has stored as much energy as it can, then it behaves like a short circuit. Okay, it behaves like a short circuit. Think of this as a pipe of water, and you wound it around in a certain loop, right? Once water starts flowing, there might be some impediment, but it goes through. And once the pipe is completely filled with water, it doesn't matter how many loops you have, water will continue to flow at a constant rate. So there is no obstruction. Unless the rate of flow of water changes, then you might see something at the output. So kind of similar to that example. Okay, unless the current changes, the inductor behaves as a short circuit. Okay, so you apply a DC voltage. Once it reaches full charge, inductor voltage goes to 0, and it behaves like a short circuit. This is an important concept. If you're taking 251, you would have already done this experiment in lab 5. In lab 5. That makes sense to everyone? Okay, di over dt is 0, and so voltage goes to 0. All right, any questions before I move on? Okay. Power is given by VI. Electrical power is always the product of the voltage and the current, VI. So simply plug in the values that we obtain for V and I for an inductor, and we get Li di over dt. Voltage is L di over dt multiplied by I, so you get Li di over dt. And then, of course, there's a derivation to determine the energy. This should be lowercase w. So we do that, do the calculation of that equation, and we obtain the energy stored in that inductor. The total energy stored in that inductor is given by the expression half Li square. Half Li square. Okay. That is the total energy stored in the inductor. Again, you don't have to memorize these equations as long as you are able to recognize and use them. So at the end of this chapter, I have a slide which summarizes all the equations related to both inductor and a capacitor. And they're duals of each other. So all of the equations are very similar. For an inductor, it's half Li square. For a capacitor, it's half CV square. Here we have voltage is equal to L di over dt. For a capacitor, it's the opposite. I is equal to CV, C dV over dt. Okay. But that's it for the equations for an inductor, right? We have voltage, current, power, and energy. Those are the three equations. Voltage, current, and power are the three main equations we care about. Yes. Mm-hmm. Absolutely. Yeah. So question being asked is, if we apply a current to an inductor in a real life circuit, we turn it on, then would we see a voltage across the inductor briefly? And the answer is yes. It'd be very, very brief. And again, depending on the size of the inductor and the amount of current that is being, sent through the inductor, it could be like a millisecond, few milliseconds, could be few microseconds, or it could be seconds. It just depends on, again, depends on the size of the bucket and the amount of, or the rate of flow of water, how long it takes to fill up. Make sense? Right. So we'd be able to see a voltage, but be very, very brief. Inductors, it can store energy and then release it all at once in one time. So one of the most common applications used to be, the chokes in a vehicle or the ignition coil, for instance. The ignition coil in a vehicle, the starter, stores a lot of energy from the battery when you first turn it on, and then it releases it all at once. Similar application for a capacitor is in the flash, or a camera flash. So even the small, well, nowadays we just, we use it on our smartphones, but we still, professional photographers use those not overhead, those flash units that go on top of their cameras. You don't know what I'm talking about, right? And so a capacitor charges using the batteries that are installed in that unit. And then when you press the flash button, all of that energy is released all at once, creating a big white light at the moment that it requires. And so those are the two applications. All right, capacitor. Capacitors are energy storage devices. They store energy in an electric field or in an electrostatic field. They are nothing but two parallel plates separated by an insulating material. Okay, there are two parallel plates. Conductor, insulator. And remember what I said about a wire. A wire inherently has resistance, capacitance, and inductance. but it does not rise to the level of interference. So you could take the two palms of your hands together, separated by air, and you could measure the capacitance between your two hands. And I mean, it's going to be very, very small, but if you had a measurement meter that is capable of measuring it, you would be able to measure capacitance that way. So again, capacitance is nothing but two conducting parallel plates separated by a dielectric or an insulating material. Symbol for a capacitor is usually just two parallel plates. Two parallel plates, again, could be drawn anyway, but they should be of equal length. Okay, they should be of equal length. Sometimes you might see like a concave line like this right here, but all of these are exactly the same. Okay, they're all exactly the same. Two parallel plates, two horizontal lines. If an arrow through a component simply means the value is changed or not changed, the value could be changed. And that is something, I don't recall if I mentioned this for a resistor, but if you have a resistor or an inductor and you have an arrow through it, the arrow simply notes that is variable. You could change the value of that component. Okay. Capacitors, like inductors and resistors, are passive components. They follow the passive sign convention or the passive reference configuration. They are not polarized. Okay. You can connect a capacitor similar to a resistor or an inductor at either end or either terminal. They are not polarized. When they receive the energy, we could say one end is positive and one end is negative, but physically you could take the capacitor out, flip it, and insert it back into the circuit, and it would still work just fine. So it's a passive component that follows the passive sign convention. Meaning, current always goes from high to low. Current will always go from plus to minus. And if you're given the voltage, then current, and if you're given the current, then the point of entry is plus and the point of exit is minus. Okay. The only exception for a polarized capacitor is a specific type of capacitor called electrolytic. Electrolytic capacitors have a very thin film coated with a very thin layer of some electrolytic gel, and you roll it up, and when you apply a voltage to that capacitor in a specific polarity, the gel oxidizes and acts as an insulator. And that is the only example of a polarized capacitor. Okay? Otherwise, capacitors do not have any polarity. So, functioning of a capacitor. Let's say you have a capacitor, you connect a voltage source to it. This is simply a switch. Remember from chapter 1. The moment you close the switch, the capacitor starts charging. What happens is that the electrons at one end of that capacitor, meaning the plate that is connected to the positive terminal of that voltage, the electrons from that plate get attracted to the positive terminal. On the other side, the electrons are repelled. Okay, so the electrons in the wire are repelled from the negative end of that voltage source. So there is a buildup of charge as shown in this illustration. When electrons leave one end of that plate, it's going to cause an extra positive charge to appear. And when electrons accumulate at the other plate, negative charge appears. And the difference in charge, of course, or difference in potential is measured in terms of voltage. So that voltage is noted as the capacitor voltage. That voltage is noted as the capacitor voltage, VC. So when you first apply a voltage to a capacitor, initially the voltage across that capacitor plates was 0 volts, but slowly the charge starts accumulating and we see a potential difference between the two plates, and we can measure a voltage between those two plates. So that voltage is simply capacitor voltage VC. When you flip the switch open after you finish the charge, you can remove the capacitor from the circuit and it would hold the charge like a battery. Again, remember, this example is for an ideal capacitor. Ideal capacitor. Ideal capacitor, we are saying if we remove it from the circuit after it finishes charge, it should hold the charge indefinitely. In real life, that's not the case. Depending on the size of the capacitor and the voltage that you apply to it, that voltage will slowly be discharged through the capacitor itself. And that is true for an inductor also, because real life capacitors and inductors do not have ideal components, obviously. So the capacitor voltage will discharge through itself. Remember, it's two plates separated by an insulating material. But in real life, there is no perfect insulator. It might take minutes or hours or days, but that capacitor will lose the charge completely because the two plates are connected. Since we say they're separated by the insulator, we can also say they are connected by that insulator. So charge from one plate would seep through and discharge from the other end. For an ideal capacitor, of course, we remove it and you can see the charge in that capacitor. There are some videos online where you can actually see they'll take charged capacitors like a big ones and take it out of a circuit once it reaches full charge, and they short the two terminals together. What do you think happens? Small spark. Well, small depends on the size of the capacitor and the voltage it's been charged to. But let's say it's a 10-volt capacitor and you charge it up and just shorted the two terminals together, all of those 10 volts is discharged all at once. You might see a small spark. But if it's a 100-volt capacitor, big ones, and you short that out, you're now discharging 100 volts all in less than a microsecond. So then you would have like a big, don't do that. All right, discharging. I just talked about discharging. Basically, you can take the capacitor out and you can short the terminals. Obviously, we would always want to use a resistor to discharge an inductor or discharge a capacitor. Once you connect a resistor through there, that resistor opposes the discharge of energy all at once. The current or the voltage will flow through the resistor slowly, and the resistor would dissipate the energy in the form of heat. So obviously, we do not want to short out a capacitor or an inductor. So capacitors, like inductors, can only store, receive energy and deliver it back into the circuit. They cannot generate any energy of their own. They store this energy in an electric field. Any questions before I move on to the equation? Okay. So the capacitance of a capacitor is the capacity to store energy, right? That is measured in terms of the charge stored for every volt applied to that capacitor. So we get the equation C equals Q over V. Or the charge is the capacitor times the voltage. Q is equal to CV. Q equals CV. And from there, we get the equation for the current and the voltage for a capacitor. Okay. Unit for capacitor is farad, named after Faraday. typical real life capacitors are on the order of like microfarads, nanofarads, and picofarads. Okay. Typical capacitor values are in microfarads, nanofarads, or even picofarads and femtofarads. This is actually a big deal. Even a small capacitance is a big deal when we talk about microchips. In microchips, we have billions of transistors. And so even if you have capacitances for each transistor, which would be in the femtofarads, which is 10 raised to minus 15, now you add hundreds of billions of transistors, all of those tiny capacitances add up. Those capacitances will short out your circuits in unwanted places. Okay, just a real life example. All right, so three straightforward and simple examples just to illustrate how the voltage, capacitance, and the charge is related to each other. So in the first example, we are applying 2 volts. We're applying 2 volts to 2 plates. The charge stored is 6 coulombs. Right? So the 2 plates can store a charge of 6 coulombs for 2 volts applied, meaning for every volt applied, it can store 3 coulombs, 3C over V, 3 coulombs per volt applied. And so it's 3 farads, 3 farad capacitor. If it could store more charge, and in the second example, the charge is doubled, 12 coulombs, then it's now 6 farads. And depending on the physical construction of a capacitor, the materials that are used, we could increase the voltage and increase the charge that is being stored. And we get, 12 coulombs and 8 volts. If we increase the voltage, now our actual capacitance, we say it's smaller. Okay. So it's 1.5 farads. So it's charge stored per unit of voltage applied. Okay, so it's indirectly proportional to the unit of voltage applied. So the capacitance we say is lower for every unit of voltage applied. So the higher the voltage, we say the capacity is lower, indirectly proportional. Physical construction of a capacitor. Again, it's 2 parallel plates. If you have something like this, both plates are the exact same size. Okay, let's say both of them the exact same size. What would you choose? Here in this equation, C is given by epsilon A over D. Okay, epsilon A over D. Epsilon is the permittivity and is given by epsilon 0 times epsilon R. Similar to the permeability for an inductor, epsilon measures the permittivity. Okay, so epsilon 0 is a constant. Oh, mu 0 is also a constant. It's 4 pi into 10 raised to minus 7. I don't know if I had that on the slide here. For an inductor, didn't have it. But mu 0 is 4 pi into 10 raised to minus 7 bursts per meter. Okay. Again, it's a constant. Maybe you might have come across it in physics. Perhaps, maybe or maybe not. And so again, you can have these values on your equation sheet. I have no problem with that. Okay, 956. And capacitor physical construction. Okay, so epsilon 0 again is a constant. permittivity of free space of vacuum in Farads per meter, and epsilon R is the relative permittivity of the insulating material relative to relative to epsilon 0. Okay. Again, it is the material property of the insulating material. So A is the cross-sectional area of the two plates, but not of both together, just that single plate. And D is the distance between the two plates. So this is D, depending on how close or far apart the plates are. Obviously, it's indirectly proportional. I mean, the farther apart your plates, the lower your capacitance, the closer they are together, the higher capacitance. That's why electrolytic capacitors, as I said, you have a long rectangular strip of conducting material, and they try to make it much thinner. So they just coat it with a thin layer of gel, and you roll it up. So when you roll it up, the distance between the two plates is very, very small. Okay, it's very, very small. And thus, you can have a higher capacitance value in a very small physical construction. So coming to this example here. This is A, this is A. Both are the same size. Where do we measure the capacitance? We need two parallel plates. So if they're crisscrossing each other, they only cross over in this area. Okay, so your capacitance is only measured in the plates crossover. Okay, yeah, remember it's two parallel plates, right? So the capacitance is only measured where the two plates cross over. Yes, sorry. Yeah. Top view. Top view. This is a real life example. Microchips have connecting wires that are completely flat. They go over from one point to another point, and there are like about 10, 12, 13, 14, 15 layers of wires running all across the place. Billions of transistors on, in a small microchip, and you have multiple layers of wires. And so each of those wires is separated by an insulating material. So you might have a conductor running from point A to point B, another conductor running from point C to point D, kind of like a bridge separated by an insulating material. And so the crossover section in that microchip is a capacitance. And so that causes issues with circuits. That's part of like circuit design. Okay, let's see, it's 10 o'clock, so we'll end class here today. If you have any questions, I'm available for the next 10 minutes. Otherwise, I will see you all on Friday. This was